Okay, question number 3. Blue light of, okay, this is for 11 marks, so I have chosen 11 minutes here. Right, let's start the timer. Blue light of wavelength lambda is incident on a double slit. Light from the double slit falls onto a screen. Pen also here. Okay. Then a student measured the distance between 9 successive fringes on the screen to be 15 centimeter. So he measures 9 successive fringes. Let me write down 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. Right? 1, 2, 3, 4, 5, 6, 7, 8, 9. Yeah. So he measures this to be 15 centimeter. So this is seen to be 15 centimeter. Okay, which means, see, if each fringe width is beta here, this beta 1 beta 2 3 4 5 6 7 8. So it is given that 8 beta is equal to 15 centimeter, or 1 beta is equal to 15 by 8 centimeter. This is what is known to us. Okay. Then separation is given as D is given, capital D is given. Explain the pattern seen on the screen. Okay, so you need to explain. So now what is happening over here? You are using a single wavelength, so interference is possible. So therefore you are getting alternate bright and dark fringes on the screen. But you cannot stop here, because for 3 marks, and here the keyword here is explain. The second point you can write is, you can say bright fringes. What is the reason for getting bright fringes? This is due to superimposition of crust from 2 slits, right? And the dark fringes, similarly, dark fringes. Why do you get dark fringes? Superimposition of crust from 2 slits. It is, or you can say, yeah, superimposition of waves out of phase. You can write like this also, out of phase. And here you can say superimposition of waves from 2 slits in phase. Okay, you can write like this also. In phase you can write 0 degrees, and here you can say 180 degrees. I think 3 points are there. I think that's sufficient for you to write it. Then calculate in nanometer the value of wavelength. So what do we have here? We already know beta is equal to lambda capital D divided by small d. So beta is already known. What's the value of beta? Beta is 15 by 8 centimeter. I'll write it down. Or first let us calculate the value of lambda. Use lambda as a subject. So lambda should be beta d divided by capital D. I will express lambda in terms of this, which should now be, this is 15 by 8, right? How much is it? It's 15 by 8 centimeter. So I'll write 15 by 8 into 10 power minus 2 multiplied by small d. What is the value of small d? Small d is already given to be 60 microns, and capital D is 2.5. This is 60. Okay, capital D is 2.5, right? Capital D, okay, I have small d here. 60 into 10 to the power of minus 6 divided by capital D is 2.5. Okay, when I do this calculation, how much do I get? So let's do the calculation. I get this as 15 into 60 is equal to so much divided by 2.5 is equal to so much divided by 8 is equal to 45. So I get this as 45 into 10 to the power of minus 2 minus 6 will be minus 8 meters, which will be around 450 nanometers. Okay, so this is the right answer. Then next one, the student now moves the screen closer to the double slit and repeats the measurements. The instruments used to make the measurements are unchanged. So what is he changing? He is only changing, repeats, moves closer to this double slit, which means what? Capital D is changed. Okay, discuss the effect of this movement on the fractional uncertainty in the value of lambda. Propagation of uncertainties. If you go to my website, you can see, okay, there are several problems. On concept-wise problems, I have put on propagation of uncertainties. So you can look into that. Okay, what does it mean? How do you get all this? Now towards it, once again, let us copy the formula from here. The formula for lambda is lambda equal to beta d by small d. So we have lambda is equal to beta d divided by capital D, and then I want delta lambda by lambda, which should be delta beta by beta plus delta d by d plus delta capital D by capital D. And what is he asking? Saying here, he says the instruments used to make measurements are unchanged. That means what? So, and then only he moves the distance here. This d is changing, this is not changing. So this tends to be 0. So you have only these two, delta beta by beta plus delta d divided by d. What is the effect of this? Now we already know beta is equal to lambda divided by capital D by small d. Now if d is reduced, okay, let me write it down here. If d is reduced, what will happen? Beta will also reduce, right? Forget about this. Lambda by d is constant. Beta will reduce. Okay, so therefore, if d reduces, beta reduces, which means these are directly correlated. And if that is the case, if b reduces, then 1 by beta will increase, right? Which means this factor will now increase. What about this factor? This factor will also increase because when d is reducing, 1 by d increases. So therefore, this will also increase. Okay, so if these two factors increases, then what will happen to delta lambda by lambda? The fractional uncertainty will also increase. Okay, so these kinds of things you should keep in mind even while you start working on your IAs also. Okay, in your IA, if you know the math behind it, it will be very easy for you to decide. Okay, so should I keep something at a much farther distance, nearer distance? You can put all this in your evaluation, right? Okay, now let us move on to the next one. The student changes the light source to one that emits 2 colors. Now you are going to use light source which are emitting 2 colors. Okay, not only one light source. The blue light of wavelength lambda and red light of wavelength 1.5 lambda predict the pattern that the student will see on the screen. What is the pattern? Now the blue light will give you a fringe width of lambda capital D divided by small d, while the red light will give you a fringe width of beta r, which is equal to 1.5 lambda capital D divided by small d, which is equal to 1.5 times beta. 1.5 times beta. Okay, beta blue, which means what? If you have, this is my screen, this is my fringe, over here. Beta blue would be, beta red would be this much. Beta red would be this much. This is your beta red. This is your beta red. Okay, 1.5 times beta blue. Where is beta blue now? Beta blue would have been somewhere over here. This could be your beta blue. So which means what is happening? Which means there is an overlap. Okay. So first thing is you can write fringe width will increase. First one. Second observation, what do you see? You can see red fringe will overlap with blue fringe. This is what can happen. Okay, as a result of it, what can you get? You can get something like a purple color, right? When a red, a blue, these two are added, then definitely we get a purple color fringe. Then next, third observation is that there's also a possibility that when, see for example, let me first write down blue fringes separately here. Okay, so I write down blue fringes here. These are all blue fringes over here. Now I will write down the red fringes. Maybe I will take up a different color pen so to illustrate that. So I'll take up a red color over here, and red color, let us say this is my central fringe over here. So as a result of it, so this is one beta, this will be the next one. See, this will now start covering like this over here. Okay, from here this is one red over here, this is another red over here. So this is one complete fringe over here. From here to here this has been covered. Then similarly this will also cover from here to here and so on. Which means the red color fringe, the red fringe will overlap with the dark fringe of blue color light, right? Whenever you say the fringe has been formed, what is that you expect? You get a bright fringe, you get a blue color fringe, and you get a black color fringe. What is black color? That is no light, right? So that's what you call as black color or no light over there. So these two should be there. But now what's happening is, at the place where there is a dark color, then this red color will go and overlap here. So as a result of it, what can you see? The contrast between a bright and a dark fringe is lost. Okay, you won't get a contrast. So as we go away, then what can happen is, as we go away from here, from the central fringe, as we go on either sides, there's a possibility that you will get an uniform illumination with different colors. You will not be able to see clearly where is a bright fringe, where is a dark fringe. That's what may happen. That's why we say coherence is required and you should use only one wavelength. A monochromatic wavelength will always give you a better sustained interference pattern, a proper interference pattern. If you have a polychromatic source, then this is what will happen, right? Thus, we have come to an end to the questions for today. So, see you next week with other set of questions. Thank you.